Good morning, my YouTube viewers. It is Crystal here, and I wanted to give you another code review. I'm doing a code review on a Kaggle competition that I completed yesterday. I worked on it all day long yesterday. If you'll notice, I got a bronze medal on it, so I won a bronze medal, and I had an 86% accuracy. And then I got one comment saying, oh, they like my code and would I please look at their code. But I generally don't look at people's codes because I just don't have the time. I'm busy doing things. So I don't have the time to look at other people's code unless I'm researching something. So this is a Kaggle Playground series, season 4, episode 2, and it's just supposed to predict on whether a person is going to be obese or not. So I've used the Flax multi-layer perceptron classifier, and I used a softmax to do that. I ran it up on Kaggle's Jupyter notebook, and it's stored in my account. One thing I will do is I will leave a link to the Jupyter notebook in the description box, so if you want to go along with me, you can. The problem statement is determine if an individual is obese or not. And then after we've got our problem statement, what we do is we import the libraries. And you notice that we had to import quite a few libraries to get this program to work. So we're importing NumPy as NP, and what that does is that creates NumPy arrays and performs numeric computations. We import pandas as PD, and that creates your data frame and processes the data. We import OS, which goes into the operating system and retrieves the files that you need. We import scipy.stats, and what we're going to do is we're going to use the Kolmogorov-Smirnov test, and then when we do it, you'll see it. I know I didn't pronounce the Kolmar correctly, but if you do a search on Smirnov, then you'll be able to get the test. We're going to import sklearn, which provides machine learning functionality, and we've got quite a few functions there. We're going to import JAX, which is a higher level numerical computation library written similar to NumPy. So if you know how to use NumPy, then you should be able to get the hang of JAX. We're going to import jax.numpy as JMP, and so what that does is that's sort of like the NumPy portion of JAX. And so if you know NumPy commands, then you should be able to use the jax.numpy commands. We're going to import Flax, which is written on top of JAX, which is a library that enables you to create neural networks. From Flax, we're going to import Linen, and that's your neural networks. From typing, import sequence and tuple, and that is a module in Python, and it's going to help you when you create your multi-layer perceptron. We're going to import Optax, which is going to get you your optimizer, because in Flax and JAX don't have optimizers in their libraries anymore. You have to go into Optax to get the optimizer. We're going to import matplotlib.pyplot as PLT. That's going to enable you to visualize your data, and we're going to import Seaborn as SNS, so that's going to enable you to visualize your data too. And then so after we have imported all of the libraries that we need to run the program, then what we're going to do is we're going to use the OS to go into the operating system and retrieve the files that we need. The files that we retrieve are train, test, and sample submission. So now what we're going to do is we're going to show all columns of the data frame. So because what it does is if you don't put in coding to show all columns of the data frame, then it won't show all the columns. So pd.set option display.max columns none, that enables you to show all the columns of the data frame. We're going to read the CSV files into the program. So when we read the CSV files into the program, we're going to make data frames. The data frames that we're going to make are train, test, and submission. So you've got the train data frame. It's got 18 columns of data. The last column being in obesity. And that's going to be your target in the test data frame. We check to see if we have any missing values. We don't have any missing values, so that's good. That means we don't have to impute anything. We want to see the unique values in the target, and you see these are the unique values in the target, and then we also want to see the number of unique values in the target, and so it's going to be 7. Now we look at our test data frame, which is 17 columns of data, which means that it is missing the target, and that's what we're going to have to make predictions on. We check to see if we have any null values, and no, we don't have any null values. And then we check submission. This is what Kaggle wants to see when you submit your work. So now what we're going to do is we're going to check to see if train and test are from the same sample. So basically what I did was I used the Kolmogorov-Smirnov test and then to check the p-value. And so if the p-value was less than 0.05, then you're going to put it in this array called drop. And we had 2 columns of data that were in the array drop. We had the ID, which you don't need your ID. And the reason why is because Pandas data frames automatically index every row of data anyway. And then you had height. And I went and looked at height. And when I looked at height, I just thought, well, I don't know. I decided I'd go ahead and leave height in there because my big concern was that you would have heights in the test data frame that were not in the train data frame. But I looked at it and the heights looked pretty similar. So I decided to go ahead and leave the height in there. But so that's why, like when you drop columns, you need to look at the columns and see how similar or dissimilar they are. And even though it had a low p-value, a p-value of less than 0.05, I decided to go ahead and leave the height in there. So now what we're going to do is we're going to analyze the target, and we use the SNS count plot, and the data frame was train, and the X value was no obesity. And then so you can see here, you can see how many you have of whether they're obese or not obese. So you had obesity type 3, and that was more than anything else. And then you had a few people who were normal weight. Now what we're going to do is we're going to label and code the target. And the reason why is because it's more difficult for the model to make predictions if it's not a number. Sometimes it does, but I just decided I could have tried it out to see if it would make a prediction, but I just decided to go ahead and encode it into a number anyway. So we check train info, and you can see all of the columns of data are either an object or a float, but also you'll notice here that what I did was I defined, when I label and coded the target, I defined the target as being no obesity, And I popped it out, and what happens when you pop it out is it just goes out of the data frame, so you don't have to drop it. So that's another thing. So that's why when we check our train data frame, we check the info, you can see that you don't have the target in there because the target has been popped out. So we want to find the unique values of each column for call and train. If train call.dtype equals object, print call train call.unique. So these are the unique values of each column. And then we check the unique values of each column in the test set. And now what we're going to do is we're going to encode each column. Now normally what I would do is I ordinal encoded it, because basically what happens if you are encoding the target, then it's going to be a label encoder, and then if you're going to encode the features, then it's going to be an ordinal encoder. But there seemed to be, like, one of the columns, I'll show you which one it was. I think it was one of these. It was either calc or CAEC. It didn't work properly whenever I said test equals enc dot transform test call dot values dot reshape -1 1. And since it didn't work, I used fit transform. But strictly speaking, what you should have done is in the train, you should have used the function fit transform, and then if you use test, you should have used the function transform. But it didn't work, and the reason why it didn't work because these the unique values were not in order. And then so I had a choice. I couldn't do anything to the data frame because the data frame was as it is. So I could have either deleted the column in question, which I think it was CAEC was the column, or I could have used fit transform. So rather than deleting the column in question and risking having a lower accuracy of the model, I went ahead and left the column in, but just used fit transform. But normally, for the test column, but normally I would use transform if it had worked properly. And now what we're going to do is we're going to do a heat map of the train data frame. And so here's your heat map of the train data frame. And you can see by looking at the heat map that all of the features have a relatively low correlation, except for a few which is a little high, but we only delete features if it has a correlation of greater than 0.95, and just by looking at the color map, it looks like there's nothing greater than a 0.95, so I didn't delete any columns that had a high feature. And sometimes it doesn't work. Sometimes you can try it out. I mean, you can delete features that have a high correlation, but you may have lower accuracy if you do that. So that's why you have to try it with not deleting the columns, and then see what your accuracy is, and then try it with deleting the columns and seeing what your accuracy is. But I didn't do that on this occasion because they didn't have a particularly high correlation. And now what we do is we define our x variables as y is your target, x is your train, and x test is test. We set up our rows and features as being x dot shape. So we standardize the x variable, and I set it up to where you could either use the standardization or normalization, but in this instance I decided to go ahead and use standardization. But what you could do if you wanted to, you could do normalization as well and see which model performed the best, because it's not going to work with no standardization, I can tell you that. but you see which model works the best. Either it's going to be a standardization or a normalization, and then use that one. That's one thing that you could do to try to improve the score. And now what we're going to do is we're going to use train test split to split the data set up into training and testing, training and validation sets. And now what we're going to do is we're going to convert the X-train, X-val, Y-train, Y-val, X-test into JAX arrays. So now they're all JAX arrays, and then you can check the shape of those arrays. And now you have something called Y-train encoded. So we're going to one-hot encode the Y variable, the Y-train variable. So there's your one-hot encoded Y-train. And we're going to define the key. That's a randomly generated number, a pseudo-random generated number, really. And so you've got your key, and then we define our MLPC, that's multi-layer perceptron classifier. So features equal sequence int 5, 10, 15 classes. And then you've got your function for your setup, and then you've got your function for your call, and then we're using the softmax activation function to get the prediction. So model equals multi-layer perceptron classifier, params equals model.init, key, comma, X-train, and then the first 5 rows. For layer params and params, params.items, print layer name, and then weights biases equals layer params, and it's kernel, and then bias, and then you're going to print your shapes and your weights and your biases there. So you've got layer 0, layer 1, layer 2, and layer 3. Layer 3 is the final layer, and it's got the classes as the number of nodes, and there are 7 classes, so that's how many nodes you're going to have. So now we're going to predict on X-train, and you can see that we've got our answers on X-train. And now what we're going to do is we're going to define our loss, and that's your loss function. And now what we're going to do is we're going to train the data into the model. So model equals multi-layer perceptron classifier, random array equals jax.random.normal, and then key equals key, shape equals 5, comma features. So that means it's going to have 5 rows for the number of features. Params equals model.init, key, comma, random array. Optimizer is going to be optax.atom, learning rate of 0.001. So another thing that you can do is you can always try a different learning rate, and that might improve your score as well. Optimizer state equals optimizer.init params. Loss grad equals jax.value and grad neg log loss. And then we're going to train for the number of epochs. For I in range 1, comma epochs plus 1. Loss val gradients equals loss grad. Params X-train, Y-train encoded. Updates optimizer state equals optimizer.update gradients optimizer state. Params equals optax apply updates params update. For I, if I is divisible by 100 equals 0, then you're going to print the loss. So you can see that we trained the data for 1,000 epochs, and you can see that the loss went down from 0.35 to 0.10. And now we're going to predict on the validation set. So you've got the validation set and the prediction. And we had 87% accuracy when we predicted on the validation set. and we created a classification report so you can see how each feature worked in the validation set. I also thought about putting a confusion matrix in there, but I thought that since it had 7 features, it would be more difficult to use the confusion matrix, but you can always put a confusion matrix in there as well. So now we predict on the test set, and then so we've got our predictions, and then we create a disk plot, and so you can see the predictions in the disk plot. And then now what we have to do is we have to inverse transform the predictions, because what Kaggle wants to see is actual predictions and not a number. And then what we do is we prepare our submission. So submission no bias dad equals preds, submission.tocsv, submission.csv index equals false. So we're creating a CSV file of the data frame. Submission.read CSV, submission.csv, and then submission. So we've converted that data frame, we converted the CSV file into a data frame, and then so you can see what the predictions are. And that's it. That's it for the code review. Now, what you could try if you didn't want to encode the target, you can try not encoding the target and see what happens, because some models will accept it if the target isn't encoded. But I just went ahead and encoded the target in this situation, and then inverse the coding at the end. But if you wanted to try it and see if it would work without encoding it, you could always try it. It won't always work. It depends upon the model whether it's going to work or not. So I'm going to go ahead and conclude this code review because I've covered everything in the code review, which is what I wanted to do. You can see that I got a bronze medal on Kaggle, and you can see I also got a comment. So I didn't do too bad. Obviously I didn't win, but I don't have time. I don't have the time to actually put into trying to get my accuracy as high as possible because I have other things to do. So I'm going to conclude this video. Thank you to my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. And thank you again for watching my video.